So with adding and subtracting radicals, you have to have like radicals. We talked about that on Friday. So the square root of 18 and the square root of 32, both of those reduce to have a radical 2 afterwards. 18 reduces to 3 root 2, 32 reduces to 4 root 2. So if you were to add those two together, 3 root 2 plus 4 root 2 is 7 root 2. You basically treat the root 2 just like you would treat a variable. 3 plus 4 is 7. Keep the radical and the radicand the same. And then if you have radicals with the same index, you can multiply them together using the product property of radicals. And this was the answer we got from that. We had to use FOIL on this. But anytime you multiply a radical with the same index value, you can multiply the numbers under the radical or the numbers in the radicand. And so that's what happened here using FOIL. None of these particular numbers could be reduced. There is no cube root factor of 12. There is no cube root factor of 42. 2 is not a cube root, neither is 7. And if you take a look at the perfect cubes, the powers of 3 on this list here, we've got 9, 27, 81, and so forth. So 42 would be kind of the only candidate to have a possible perfect cube factor. But 42 is not divisible by 27, nor is it divisible by 9. Therefore, there are no perfect cube factors of 42. So there's nothing that we can do to simplify that. So our first actual example that we're going to work through is this one right here. So it says factor using squares. Basically, what it's telling you to do is simplify under the radicals first. That's what that means. Factor using squares, simplify under the radicals. Page here, and then just a reference paper. All right. So for this first problem, simplifying underneath the radicals, factor using squares, same thing. If you look at the square root of 45, if you look at the perfect squares list here, powers of 2, which of those numbers is 45 divisible by? Sorry, perfect squares would be across the top row, not powers of 2, but perfect squares are the ones across the top row. Sorry. I was looking at things the wrong way, but yeah, look at left to right, not top to bottom. So perfect squares, which one is divisible? Which one can you take 45 and divide by? 9. 45 is divisible by 9, which is 3 squared. So underneath here, we can write 3 squared. Because 3 squared is 9. What is the perfect square factor of 12? What number that multiplies by 3 is equal to 12? Because it tells you the other factor, 4. And 4 is the perfect square of 2. So we can write 2 squared. Or you could write 4 there, either way. And then what number goes here? Two squared or 4. Yeah, either way. 2 squared or 4. All right. Then what it's doing is it's using the product property of radicals to break apart each of the radicands. Because if you have a square root of 3 squared times 5x, you can break that apart into the square root of 3 squared times the square root of 5x. Same thing here, square root of 2 squared times the square root of 3. Same over here, the square root of 2 squared times the square root of 5x. The square root of 3 squared is what? 3. And then under the square root over here, the radicand is still 5x. So we just write 5x under the radical there. Here we have 2 times the square root of 3 because the square root of 2 squared is 2 times the square root of 3 gives us 2 root 3. And then over here, what's the value in front of our radical? 2. Okay. And what's underneath it? 5x. All right. Then it just says, so simplify radicals here. Then it says to multiply, because if you have 6 times 3 times the square root of 5x, you can multiply 6 times 3 together because we just have regular coefficient values, and 6 times 3 is 18. So we get 18 there. The 2 root 3, we can drop the parentheses because there's nothing to simplify there. And then over here, we can multiply 3 and 2 to get 6. So that'll be minus 6 times the square root of 5x. And then simplify here means to combine like radicals, which is the same thing, same process as combining like terms. You basically say, all right, which of my radicals is the same with the same radicand? And that would be this square root of 5x and that square root of 5x. And we've got an 18 here minus a 6 here. What's 18 minus 6? 12, exactly. So the answer is 12 times the square root of 5x plus 2 times the square root of 3, or 12 root 5x plus 2 root 3. Are there any questions about our process here before we continue? All right. Let's try the next one. Might need to use a little bit of space off to the side, but if we write small, I bet we can make this work. So I'm not going to write the answer on this line, by the way. I know it wants us to, but we need to have a little bit more room to work that out. Okay. Let's take a look at our indexes first. What's the index of this first radical? 2. What about this one? 2. What about that one? 2. This one? 2. So the indexes are all the same, which means we have the potential for 4 like radicals. They might not all be like radicals at the end. They probably won't be, but the potential is there. The square root of 18, there is no, 18 is not a perfect square, but there is a square root factor of 18. What is it? 9. Okay. Now, again, this is a situation where I'm not going to write that many steps. I feel like that's a little bit overkill, which is, it's fine that we can see all the details here, but I do not expect you to do that many details when you do this problem. Because the square root of 18 factors to the square root of 9 times what equals 18? 2. So that'd be the square root of 9 times the square root of 2. What is the square root of 9? 3. So we could just go ahead and write 3 root 2x. That's what the square root of 18x turns into. What is the perfect square factor of 28? Because 28 is not a perfect square. What perfect square number is 28 divisible by? It divides by 7, and the other factor would be the perfect square, which is 4. What's the square root of 4? What's 2 times 5? 10. So that'll be minus 10 root 7. So we can do multiple steps before we actually write something down. Yeah. And then over here, 98. What perfect square factor is 98 divisible by? This is where this particular paper could come in handy, because perfect squares are across the top here. Which one of those numbers is 98 divisible by? In that top row. So the numbers that are less than 98 would be 81. 98 is not divisible by 81. Is 98 divisible by 64? No. Is it divisible by 49? Yeah. 49 times what? 2. So this would be the square root of 49 times the square root of 2. What is the square root of 49? 7. What's 7 times 3? 21. So minus 21 root 2x. And then here we're going to have plus 3 root 7x, because 7 is not a perfect square, and it also doesn't have any perfect square factors. So we're going to say plus 3 root 7x. Okay. Now we look for like radicals. Do we have any like radicals here? If so, what are they? Yeah, the root 2x's, right? Those root 2x's are able to be put together. What is 3 minus 21? Negative 18. Yeah, so we're going to have negative 18 root 2x minus 10 root 7 plus 3 times the square root of 7x. And that should be the final answer on it. Because we only ended up with one actual like radical. So all right. Let's try another one. So this next one is our answer, by the way. This next one, we're not actually going to be, well, we might be looking for like radicals, but at least not initially. Because this time we're not adding or subtracting radicals, we're multiplying. So you can multiply radicals if the index is the same. And because this index is 5 and that index is 5, that means we can go ahead and multiply the radicals. Not only can we multiply the radicals, we can also multiply together the coefficients. So what number goes in the blank here? 3, yeah. So the coefficients here are 4 and 3. Those are our regular numbers. They can multiply at the front of the radical. So that'll just be 4 times 3 times the 5th root of negative 10x squared y to the 6th times 16x to the 4th y to the 4th. 4 times 3 is 12, so we're going to write a 12 here. And it's getting, I mean, you can see here that it's really starting to get things separated out. It's separating things out into individual factors, right? These are the base factors of negative 10. 2 times 5 is 10 times negative 1. So basically, it's factoring everything into its prime factors. However, the 16 is going to be written a little bit differently. 16 is 4 squared. However, 16 squared doesn't really match up well with the 5 here. Now, neither does the next number that we're going to write. However, there is going to be something that we can actually do on the next step where it says to group into powers of 5. Do you see 16 somewhere on the row that isn't squared? What other power can 16 be written in as a power of what? 4 to the power of 2, sure, but 16 is also equal to 2 to the power of 4. So we're going to write 2 to the power of 4 here. So this would be the prime factorization of 16, by the way. Because 4 squared would be 4 times 4, but 4, each of those 4s has a factor of 2. So you'd have 2 times 2 times 2 times 2. So instead of writing out 2 times 2 times 2 times 2, we're just grouping all those 2's together as 2 to the 4th power. So it's still prime factorization. It's just written as a power instead. All right, then once we've done our prime factorization, it says to group into powers of 5. Why would we group into powers of 5? What's the significance here of grouping into powers of 5? Yeah, the index. If the index is 5 on the radical, we want the exponents under the radical to be in groups of 5 as well. So the negative 1, can't do anything about that. However, the 2 times 2 to the 4th, we can add the exponents there. This one has an exponent of 1. That's an exponent of 4. 4 plus 1 gives us 2 to the 5th power. So there's an exponent of 5. Times 5, not going to help. If we add the x's together, 2 plus 4 is 6. But then if we group into powers of 5 or factors of 5, x to the 5th and x would be the way to split that apart, because 2 plus 4 is 6. Take away 1 from 6, you get 5. And then you have 1 left over, factor of 10. With the y's, 6 plus 4 is 10. 10 is a power of 5, or 10 is a factor of 5, which means it will cancel out with the index out here. So we're basically just kind of doing the same thing we did on Friday, where we're trying to group things together to make sure that we can cancel the exponents underneath with the index on the outside. And then we can group these. We got 12 times the 5th root of negative 1. So now you're going to use the product power of radicals by splitting everything apart. So the 5th root of negative 1 times the 5th root of 2 to the 5th times the 5th root of 5 times the 5th root of x to the 5th times the 5th root of x times the 5th root of y to the 10th power. And then it says to simplify. The 5th root of negative 1 is negative 1. Negative 1 multiplied by itself 5 times is negative 1. So that actually is a perfect fit. Negative 1 is also a perfect fit, which technically means we could have written a little 5 right next to it right here if we wanted to as an exponent. The 5th root of 2 to the 5th power is 2. The fifth root of 5 is the fifth root of 5. So that doesn't change. The fifth root of x to the fifth power is x. The fifth root of x is just the fifth root of x, so that doesn't change. And then what's the fifth root of y to the 10th? Y squared, yeah. So with these ones here, the variable or the exponent here can divide by the index here, because y to the 10th power is y squared times y squared times y squared times y squared times y squared. So y to the fifth root of y to the 10th is y squared. And then we simplify. 12 times -1 is -12. -12 times 2 is -24. Our variables, we have x here, we have y squared here, so xy squared. And then what do we have left under the radical? What's our radicand? 5x. Yeah, those are the two things that were left there. They share the same index, therefore they can be grouped together under the same radical. All right. Now, there's a little study tip off to the side here. Basically, it's a hint. It says if a radicand has a negative constant, if you have a negative number underneath your radical symbol, it may be helpful to use -1 as a factor. That's what happened over here. -1, factor that out. Then you can simplify the nth root of -1, which will be -1 if the index is odd, which happened here. The fifth root of -1 is -1. The cube root of -1 is -1. The seventh root of -1 is -1. Or if it's even, it'll be I. Because square rooting or fourth rooting or sixth rooting a negative gives you an imaginary value. All right, let's try the next one. Write the simplified form of this. So first thing we can do is write everything under the same radical and then group the coefficients off to the side. So multiply the 5 times 3. That'll give us 15. Let's just go ahead and start with that. 15 times the fifth root of everything here multiplied together. Now, what I'm going to do is I'm going to go ahead and break things down to their prime factors all at the same time. So this will be the fifth root of the prime factorization of -9. Let's factor out the -3 from that, or not the -3, the -1. And then what are the two prime factors of 9? 3 and 3, which would be 3 squared, right? So -1 times 3 squared. I'm going to do the same thing with the 27 next, just so I can put all my coefficients under the radicand together. What's the prime factorization of 27? Yeah, 3 times 3 times 3, which is 3 cubed. So 3 squared times 3 cubed. So there's 9 multiplied by -1, that's -9. 3 cubed, there's that 27. And then I'm going to go ahead and add together the exponents with the variables underneath here. 3 plus 4 is 9, so that'll be x to the 9th power. 3 plus 4 is 7, so that'll be x to the 7th power. It's Monday, I'm sorry. 3 plus 4 is 7. 5 plus 5 is 10, so it'll be y to the 10th power. Thanks for keeping me honest there. All right. So that's what we're going to get with our first step. So basically, you can see we're doing a lot more per step than what the original notes said. The original notes are just saying, it's just showing us every little thing that's happening, but we are welcome to combine things together when we can. So underneath the radical, let's go ahead and group some things together now. The -1 can stay by itself. The 3 squared times 3 cubed, though, can turn into what? 3 to the 5th, yeah. So this is going to be equal to 15 times the 5th root of -1 times 3 to the 5th power. And then let's break apart x to the 7th to have a perfect fifth. What would that look like? Yeah, times x to the 5th. times x squared, and then times y to the 10th power. All right. I'm not going to use the product rule of powers here. I'm not going to write it out as the fifth root of every separate thing underneath the radical. So what I'm going to do is just fifth root the things I can fifth root, and then leave whatever needs to remain under the radicand under the radicand. So that'll be just done down here at the bottom. So this is going to be 15 times the fifth root of -1 is -1, so times -1. What's the fifth root of 3 to the fifth? 3, so times 3. What is the fifth root of x to the fifth? Times x. Fifth root of x squared. No, that doesn't work. Fifth root of y to the 10th. Y squared, so times y squared. And then that'll be times the fifth root of x squared. Because that's the only thing that's going to be left under the radicand. Everything else was a perfect fifth and could cancel out with our index. So then the last thing we need to do is just multiply our coefficients together on the outside. So 15 times -1 times 3, what does that equal? -45. So the answer here, -45 x y squared times the fifth root of x squared. And we're able to do that pretty compactly. We don't need to write out, 6 or 7 different lines to get our answer. You're welcome to combine things in terms of steps. Okay. Any questions here? A lot of this, honestly, is using the rules that you learned in Algebra 1 combined with simplifying radicals. So let's keep going. Hey, this time we actually have like a application problem. Here we go. So we're going to use the distributive property to multiply radicals. It literally tells us what we're going to do here. So we will be using the distributive property to multiply radicals together. A sports pennant has the dimensions shown. Find the area in square inches. So it is triangular in shape. The base of that triangle is 3 root 8 plus 4. The height of that triangle is 7 root 8 plus 6 root 3. So here's the base. Here's the height. And it's quite kind. It tells us or reminds us what the area of a triangle is equal to. Area of a triangle is equal to half times the base times the height. So the area is equal to 1/2 times the base of 3 root 8 plus 4 times the height of 7 root 8 plus 6 root 3. So that first fill in the blank, 7 root 8 and 6 root 3. So if we're multiplying these together, we need to get rid of the parentheses. And the way to do that would be to use FOIL. And so that's what it's showing on the next step. First times first would be 3 root 8 times 7 root 8. There it is, 3 root 8 times 7 root 8. The outer terms, 3 root 8 times 6 root 3. That's it right there. The middle terms, 4 times 7 root 8. The inner terms, that's I right there. And then the last terms, 4 times 6 root 3. So it's just showing you the multiplication. Then it's going to combine things. So multiplying 3 root 8 times 7 root 8, 3 times 7 is 21. Root 8 times root 8 is root 8 squared, which is just going to be 8. The next one's 3 times 6 is 18. Root 8 times root 3 is the square root of 24. 4 times 7 is 28 times the square root of 8 is 28 root 8. 4 times 6 is 24 times the square root of 3, which would be 24 root 3. So multiplying after FOILing. If I was doing this, I would go straight from this step here to this line that we're at right now. I would not write everything out like that. It's just showing you what's happening. All right, then it's going to do some prime factorization underneath the radicals. So the square root of, well, 8 times 8 is squared.
Please, so it's time to release girls golf to go out to their game today, their match. Please make sure girls golfers, you come to the attendance office and check out before you leave.
So 21 times the square root of 8 squared, that doesn't change. Underneath here, the perfect square factor of 24 is 4. So that would be 4 times 6, or 2 squared times 6. The perfect square factor of 8 is also 4. So that would be 4 times 2, or 2 squared times 2. And then over here, nothing changes because the square root of 3 doesn't have any perfect square factors. The next line, 21 times the square root of 8 squared plus 18, then it's just breaking it apart using the product, the radical product property, which again is important to know, but it's not something that we're usually going to write out. I wouldn't write out this line here if I was doing this problem. I would go straight to this one here. So we have 21 times the square root of 8 squared. What's the square root of 8 squared? 8. Okay. So this will be 21 times 8. Next. Plus, what's the square root of 2 squared? 2. So 18 times 2 root 6. 28 times the square root of 2 squared times the square root of 2. Again, this is 2, so 28 times 2. This is not a step that I would actually write out if I was doing this problem. I'd probably do the multiplication and go to the bottom line here next. And then what goes on this line? On the end. 24, yeah. There's nothing to do on that last one. Okay. All right, then. Or maybe it did want the answer to the multiplication here. Oh, either way. What's 21 times 8? $168. Okay. What's half of 168? 84. All right. So 84. And then it says plus 18 root 6. How do we get 18 root 6 here from 18 times 2 times the square root of 6? From this line to that line. Yeah. Why is the 2 gone? Yeah, because of the half. Or you could say 18 times 2 is 36, and then half of 36 is 18. Either way, but that's how we get that number. 28 times 2. What's half of 56? Brings it right back down to 28. So then 28 root 2. So that number, 28. And then 12 root 3, because half of 24 is 12. There are no like radicals to combine on this one, which isn't a problem. It just kind of is what it is. So the area of the pennant is 84 plus 18 root 6 plus 28 root 2 plus 12 root 3 inches squared, or about how many square inches? Like if you were to actually type that into your calculator, give me an approximation to the nearest single decimal place here. Okay, and then if you round that to a single decimal, what would it be? Yeah, 188.5 inches squared. Cool. Nice. So we are getting relatively close to a little bit of work to do. This is a long lesson. All right, let's keep going. So a rectangular pool safety cover, the shape of this is important. Rectangular pool safety cover has a length of 7 root 10 minus 4 feet in the width of 6 root 10 plus 8 root 5 feet. Which expression represents the area of the pool cover in simplest form? We've got plenty of room off to the left here to go ahead and write this out. So let's do the work over to the left, and then we will choose the appropriate answer, A, B, C, or D. First of all, if we're looking for the area of a rectangle, what are we doing here? How do you find the area of a rectangle? What's the generic formula? Yeah, length times width. So we're going to multiply together 7 root 10 minus 4 and 6 root 10 plus 8 root 5. So here we go. We are going to get 7 root 10 minus 4 times 6 root 10 plus 8 root 5. All right, I want you to work through that one. And figure out what the answer is going to be. Use FOIL on this one, by the way. Thankfully, you don't have to multiply by 1/2. Which pretty much should be straight up FOIL for the most part. Another minute here, and then we'll see how it went. All right. You think they have it? Who wants to be brave? You got a 1 out of 4 chance here. Hopefully you have a better than 1 out of 4 chance. If you solved it correctly, you've got a 1 out of 1 chance. Any thoughts? Somebody's got to have answered it. It is not D, but D is the second most accurate one on here. It is C. Yeah. The answer is C. Here's the thing about D. D is interesting because D isn't completely wrong at all. It's just not completely simplified. this is right, but the square root of 50 does simplify. So that's the only thing about D that doesn't work. A and B are incorrect. And then, yeah, actually, all of them have parts that are somewhat correct, I should say. Now, if we think about this, so I'm gonna show you the FOIL process for this and show you what it ends up looking like. But because it's multiple choice, if you do a little bit of mental math, you can kind of eliminate some ones pretty quickly that aren't correct. Because if you look at the first terms here, 7 root 10 times 6 root 7, 6 root 10. 6 times 7 is 42. Root 10 times root 10 is 10. 42 times 10 is 420. So the first term has to be 420, which eliminates B right away. And then I looked at the last terms. So last times last, negative 4 times 8 root 5. Negative 4 times 8 is negative 32 times the square root of 5 would be negative 32 root 5, which eliminates A because that says plus 32 root 5. Then we just have to figure out what's going on in between because the first and the last terms we know are correct here. So the inner terms, now I'm just going to go ahead and do FOIL to figure out the rest of it. So we know the first one is going to be 420. The outer terms, 7 root 10 times 8 root 5. 7 times 8 is 56. Root 10 times root 5 is root 50. So that'll be plus 56 root 50, which is exactly that. Then the inner terms would be negative 4 times 6 root 10. That would be minus 24 root 10, which is exactly that term right there on both of those. And then we know that the end is going to be minus 32 root 5. So the only thing that needs to happen is to simplify this. The square root of 50 has a perfect square factor of 25. The square root of 25 is 5. 5 times 56 is 280. So we get 420 plus 280 root 2 minus 24 root 10 minus 32 root 5, making the answer C. Cool. That's the answer for that one. The last thing that we're going to be working on here is called rationalizing the denominator, which we've already done. So this is going to be more of a reminder than anything. The only thing that we haven't done with rationalizing the denominator is if you have a sum or difference of radicals on your denominator, in which case we're going to need to do use something called the conjugate, and I'll show you how to do that. It uses FOIL, but I'll show you what to do when we get there. So the bottom of this page. Any questions here before we continue? All right, bottom of the page. A radical expression, if a radical expression contains a radical in the denominator, you can't leave it because to be simplified, you can't have a radical in your denominator. You can rationalize the denominator to simplify the expression. Recall that to rationalize a denominator, you should multiply the numerator and denominator by a quantity, the same quantity, because if you're going to simplify an expression, the only way to keep it the same is to multiply by the same on the top and the bottom, because that means it's one, just a unique form of it, by a quantity so that the radicand has an exact root, meaning you won't have a radical on the denominator. So if the denominator is a square root, then you would multiply the numerator and the denominator by the square root of whatever that number is. Because if you multiply a square root by itself, you create a perfect square. So if you have 4 over the square root of 7, we've already done stuff like this. If you have 4 over the square root of 7, to rationalize the denominator, get rid of the root 7 on the denominator, you'd multiply both numerator and denominator by the square root of 7, because when you multiply a square root by itself, this would be the square root of 49, which is equal to 7. And then on the numerator, you get 4 times the square root of 7, and that would be your answer. Now, if it's anything other than a square root, for example, the nth root of b to the x power, you would multiply the numerator and the denominator by the nth root of b to the n minus x power, which that's just a kind of generic algebra complicated way of saying complete the perfect nth power under the radical. That's what it's saying. So if you have the fifth root of, the fifth root of 2 on your denominator, right here, you have 1 factor of 2 in your radicand, which means you need how many more factors to create a perfect fifth? If you have 1 out of 5 factors, how many more do you need? You got 1 out of 5. How many more do you need? 4. So you multiply by the 5th root of 2 to the 4th. So the 5th root of 2 times the 5th root of 2 to the 4th would be the 5th root of 2 to the 5th, which is 2. And so that's all it's saying here is that if your index is 5, subtract the exponent that's with the radicand already. The exponent that's with the radicand down here is 1. If you take your value of n and you subtract 1, you get 4, which means that's what you need to multiply, the 5th root of 2 to the 4th, in order to make that perfect fifth on your denominator. And so that's the idea here. Now, with binomials, we'll talk about this on the next page, but with binomials, if you are adding radicals or subtracting radicals, where a, b, c, and d are rational numbers, these would be considered conjugates of each other. Multiplying the numerator and denominator by the conjugate of the denominator will eliminate the radical from the denominator of the expression. I'll show you what that looks like on the next page. But this is basically creating a difference of squares. If you remember difference of squares using FOIL, that's what we're going to be doing on the next page with that. But let's start with just rationalizing the denominator over here first. So again, there's a lot of steps here. I will not expect you to do that many steps every single time. That's kind of ridiculous. That's like 8 or 9 lines. It's just showing every little detail along the way. So if you have the cube root of 250 a to the 6th power over 7a, you can use the quotient property to break it apart into 2 radicals, the 5th root or the 3rd root of 250 a to the 6th divided by the cube root of 7a. Now on the denominator, it's factoring it into cubes on the numerator because we're going to have to simplify this anyway. There is a perfect cube factor of 250, and if you take your chart that I gave you today, we're looking at perfect cubes here. So that would be the second row. The number of these perfect cubes that is divisible by 250 is 125. 250 divided by 125 is 2. The cube root of 125 is 5, or 5 cubed. And so that's why it says 5 cubed times 2. And then a to the 6th power is a perfect cube. It's a squared cube. So it's starting to simplify the numerator ahead of time, which is fine. You don't have to do that on this step as long as you do it in general. And so it's just simplifying the entire numerator first, which is not a bad idea to do. Because if you can simplify things before you rationalize the denominator, before you multiply the numerator by something, it might make it easier in the long run. So that's why it's doing that. So the cube root of 5 cubed is 5. The cube root of a squared is a squared. And the cube root of 2 is the cube root of 2. So it's just simplifying the numerator to get 5a squared times the cube root of 2 over the cube root of 7a. Now, it's going to rationalize the denominator. So 7 here technically has an exponent of what? What would the exponent of just 7 be? 1. What would the exponent of just a be? 1. We need to have an exponent of what in order to cancel out with the index? 3. How many more factors of 7 do we need? 2. How many more factors of a do we need? 2. So the numerator and denominator will be multiplied by the cube root of 7 squared a squared. Cube root of 7 squared a squared. Multiplying by the cube root of 7 squared a squared on the numerator and denominator is the same thing as multiplying by 1. It's just a unique form of 1, so it's not changing their value. On the denominator, those are all going to cancel out and leave us with 7a eventually. It's just showing the multiplication first, though. So if you multiply the cube root of 2 times the cube root of 7a squared, that's the cube root of 2 times 7 squared a squared. All right. So on the numerator, you get the cube root of 98a squared. 7 squared is 49. 49 times 2 is 98. That's where that comes from. A squared is just a squared. On the denominator, we get 7 cubed a cubed, which we knew all along because that's the only way to actually get rid of the radical on the denominator, making it 7 cubed. The cube root of 7 cubed a cubed is 7a. Because the exponents in the index will cancel each other out. And then if you look at 98, 98 does not have a perfect cube factor. If it did, we would deal with it, but 98 does not have a perfect cube factor. It's not divisible by 64 or 27 or 8. Those would be the perfect cubes that are less than 98. It's not divisible by any of them. And then at the end, the a on the denominator actually goes away. How come? Yeah, it cancels with the a squared on the numerator. So you got to consider at the end here, if that 5 and that 7 could be reduced, if 5 sevens could be reduced, we would reduce that. A squared divided by a does simplify. So we have a on the numerator here, and then the a on the denominator cancels out. So 5a times the cube root of 98a squared over 7. All right. Let's continue. So first thing we're going to do here, use the quotient rule, quotient property of radicals, to break apart our square root. So that'll be the square root of 20b over the square root of 3b to the 5th power. Actually, I'm going to change that a little bit. I'm going to say 20 over 3b to the 4th power. Everybody okay with that? 20 over 3b to the 4th power, because I'm simplifying these ahead of time. So if there's b here and b to the 5th down here, that one cancels out and that one becomes b to the 5th. So that's what's happening between here and here. The reason why I'm doing that is because that'll make the denominator a lot easier to deal with, because let's look at the numerator first though. Is there a perfect square factor of 20? What is it? 4. What's the square root of 4? 2. And then root 5 is what we have left. Good. So 2 root 5 on the numerator. And then on the denominator, b to the 4th power is a perfect square. What's it the perfect square of? What's the square root of b to the 4th? B squared. So on the denominator, we should have b squared times the square root of 3. So had we left this b to the 5th power, we'd have more work to do on the denominator because 5 is not divisible by 2, but with canceling out the b on the numerator and reducing the denominator to b to the 4th, that becomes a perfect square, which means we don't have to worry too much about the variable. We don't have to worry at all about the variable on the denominator. So what are we going to multiply the numerator and the denominator by in order to rationalize the denominator? What exponent do we need in order to cancel out with the square root? Squared. Okay. We have an exponent of 1, so what are we going to multiply by? Yeah. Multiply the numerator and denominator by the square root of 3. Multiply by root 3 over root 3. So on the numerator, 2 times the square root of 5 times the square root of 3. What's 5 times 3? 15. So this is going to equal 2 root 15 over, what's the square root of 3 squared? 3. So that'll be 3b squared on the denominator. The last couple things that we should look for is, can we cancel anything out on the numerator and denominator in terms of our coefficients? 2/3 doesn't reduce. There's no variable at all in the numerator, so we can't do anything with the b squared. And then, does 15 have a perfect square factor? No. All right. Which means that's our answer. So we've satisfied all the rules of simplifying radicals. So there's our solution. Questions on that one? Before we look at the last example, we're almost done with this very long lesson. Only half a page to go. One more problem. 2 more problems, sorry. We got the example and then the last one to do on your own. So last type of problem, how about that? So using conjugates, all right. Something I want to remind you of here. If you think about the rules of like properties of exponents and polynomial properties in particular. If you have something that looks like a squared minus b squared. Go ahead and write this down. This is what's known as a difference of squares. We have seen this plenty of times. Difference of squares. We used this with factoring not too long ago. Does anybody remember what a squared minus b squared factors to? We get two sets of parentheses. Anybody remember what that factors to? I'm gonna go back to beginning of module 6 here, because I feel like maybe we wrote it down earlier in this unit. I don't exactly remember. Maybe we did, maybe we didn't. We did perfect square trinomials, but I don't see difference of squares. All right, that's okay. So a difference of squares. We have not written this one down yet. A difference of squares factors to, you might remember this, a plus b times a minus b. Square root the first term, that's the first term in each set of parentheses. Square root the second term, that's the second term in each set of parentheses. One gets a plus, one gets a minus. The reason for that is if you FOIL this out, you get a squared minus ab plus ab, which means they cancel out, minus b squared, which would end up back at a squared minus b squared. And that's exactly what we're creating when we use conjugates. That's the reason why I'm referencing that here. So a conjugate basically creates a difference of squares, which will simplify your denominator to get rid of a radical here, because we can't just multiply the numerator and the denominator here by the square root of 7, because if we did, it would have to distribute to the 2 root 7, which would get rid of the root 7 here, but then we'd have to distribute to the -5, and distributing a root 7 to a -5 just creates another radical, which doesn't help. So to rationalize the denominator, multiply the numerator and the denominator by the conjugate of 2 root 7 minus 5. And so this is like the subtraction part. This is the minus part of a plus b times a minus b. So you can think of 2 root 7 minus 5, the current denominator, as a minus b. We want to multiply the numerator and denominator by a plus b, which would be 2 root 7 plus 5, which is the conjugate. So here, we're going to multiply by 2 root 7 plus 5 over 2 root 7 plus 5. And I'm going to put that, I'm actually just going to put a whole bunch of stuff in parentheses here, because on the numerator, we have to use the distributive property. On the denominator, we have to use FOIL. Again, this is going to go through all the little details, but because multiplying by a conjugate gives you a difference of squares, there's a much faster way to do this, and I'll show that once we get to the end of this problem. All right, distribute. 4x times what? What goes here? If you distribute the 4x on the numerator, what are we multiplying by first? Root 7. Yeah. And then the 4x also multiplies by the 5. So this is 4x right there, plus 4x times 5. On the denominator, it's using FOIL. So the first terms would be 2 root 7 times 2 root 7, which is 2 root 7 squared. The last terms would be -5 times 5, which is, there's that -5 times 5. The outer terms would be 2 root 7 times 5. So 2 root 7 times 5. The inner terms would be -5 times 2 root 7. So there's the minus, here's our 5, and then 2 root 7. On the numerator, 4x times 2 root 7. 4 times 2 is 8. 8 times x is 8x. 8x times root 7 is x root 7. Also on the numerator, 4x times 5 is 20x. On the denominator, what's 2 root 7 squared? Was it? Close. We have to apply the square to the 2 as well. So this will be 7, because 7's square root of 7 squared is 7. 2 squared is 4. 4 times 7 is 28. Yeah. So the squared applies to both the 2 and square root of 7 squared. So 28. And then over here, minus what? What goes on the end? 25, minus 25. Nice. Now, what happens? So in the middle here, by the way, 2 root 7 times 5. 2 times 5 is 10. 10 root 7. Negative 5 times 2 root 7. Negative 5 times 2 is negative 10 root 7. What happens to those two terms? They cancel out. Those are like radicals. 10 minus 10 is 0. Those cancel out, which is exactly what happens when you have a difference of squares. And so you end up with a squared, 28, minus b squared, 25. What's 28 minus 25? 3. That's the answer. So here's the thing. With the denominator, you could go from here straight to there. The denominator, you can go from the multiplying the conjugates straight to the end of the denominator, if you remember how to use a difference of squares. If you don't, just use FOIL and go through this process. That's totally fine, but there is a quick way to do it. If you square that term, 2 squared is 4, square root of 7 squared is 7, 7 times 4 is 28. Negative 5 times 5 is negative 25, 28 minus 25 is 3. Because the middle terms will cancel each other out. The O and the I in FOIL, when it's written like this, will always cancel out. So let's try this last one. Okay. What are we going to multiply by here on the numerator and the denominator? Yeah, 4 root 5 plus 4. Good. So multiply by 4 root 5 plus 4 over multiplied by 4 root 5 plus 4. Okay. So let's work out the numerator here for a second. 6x times 4 root 5. What's that going to be? 6x times 4 root 5. (24x root 5). Yeah. 6 times 4 is 24, times x is 24x, times the square root of 5 is 24x root 5. 6x times 4. 24x, yeah, so plus 24x. Okay, divided by. Now, let's see if we can do this in one step. That'd be kind of nice, because then we wouldn't have to use 4 or 5 different lines here. 4 root 5 times 4 root 5. So square that. What's 4 times 4? 16. Root 5 times root 5 is, they cancel, so it's 5. All right. What is 16 times 5? 80. Okay. What is negative 4 times 4? What is 80 minus 16? 64. So the denominator no longer has a radical. All right, now, are we done? Not quite. Yeah. There's one more thing we can do. The root 5 up here doesn't simplify. However, 24, 24, 64. Those all have a common factor. There's a bigger one. 8. These are each divisible by 8. What's 24 divided by 8? 3. So we can have 3x root 5 plus 3x over what's 64 divided by 8? 8. 3x root 5 plus 3x over 8. And that's the answer to that. You made it. All right. We still have about 7 minutes left, so